Yes, thank you very much for the introduction. It's pleasure to be here and to give these lectures. The goal is to explain to you how the frequency method works, show a couple of examples of how it works, and hope that you will produce many other examples how to use frequency method in predictive PDEs. One of the goals that I hope to get to is to go through an argument of Lagrange-Bartorta on the estimate of the critical set of solutions to predictive PDEs with bounded frequency. And there are many questions that are left there. What can you do? How can you prove this bound and so on? But we'll start today with a very simple things and try to build gradually our understanding of the frequency function. The frequency function itself goes back to what's it from, but in this context, I think one of the most influential papers was by Garofalo and Bean in 1986, where they used the frequency function to prove new results on unique continuation for the PDEs. I will make my life and your life very easy in this course, and I will talk about harmonic functions. I will do the computations and define the things in harmonic functions a couple of times, indicating what is different if you talk about PDE. And some of the statements I will tell you, you can prove in a different way using the function as harmonic. Harmonic is very good. It's almost knowledge. So there are many tools there that are different. But our aim is to use only the tools that you can extend to the case worlds. So what is the frequency function? I will have a harmonic function in a ball, and when I'm saying that there is a harmonic function in a ball, I always mean that it's defined in a big larger ball. So you can get the bar bracket if you want. And for each R, we look at the average of U over the corresponding sphere. So H. Sometimes it's easier to work with spherical averages, sometimes with wall averages. So I will have at least two frequency functions. The other one I will denote by the lower H. This is always the average integral. And for both these functions, we're going to do the following construction. We will take the logarithmic derivative of this function h and then override it. So the frequency is a derivative in R of the average over the average. You can check that this is I should take away the averages. That this ratio is like that. So this is what we call the frequency function. And in this case, we'll, in the same way, define the low frequency function. And let me use the fact that I'm talking about harmonic functions now. So I'll take the expansion of the spherical harmonics of my U and write these quantities using these coefficients. here yk is a homogeneous harmonic polynomial of degree d, then it's easy to check that is also normalized. Like that. Then the frequency function using these coefficients is the following ratio. And you can easily compute this one. They're very similar. What does it tell you? This implication, first of all, we see that if we take x y max 0 and take the radius that goes to 0, the limit of this is 2 times the vanishing order of our harmonic function at 0. The limit is the same for the lower frequency, and I just want to introduce both because at some points it's easier to use averages over the ball. What is also true is that the lower frequency is less than or equal to the frequency, and on the other hand, for any positive epsilon, you can find the constant surface. This is good. So they're philosophically the same, but sometimes they have to be more careful. And the whole frequency method is used on a very nice observation that for harmonic functions, this frequency is an increasing function in the radius. If you look at this expression, it's not difficult to note that the derivative in R of our frequency function is omega. And this is the main starting point for the whole theory. It's a simple exercise to prove that this is the case for a function like that. If you take one term with just constant function in R, and you can check that you have two positive functions H with this property, and the linear combination of those is also this property. And this is equivalent to the following convexity of the averages. So H where R is like that. I place between 0 and 1, and 0, 1 is not 0, 2, it doesn't matter which one, sometimes small. So what is written here is if you look at the function t to h, and you'll see this is a convex function in t. This is exactly the second derivative of this. I promise that we're going to talk about things that are still true when we go from harmonic functions to elliptic equations, definitely this is too much to be true. But what we can do for elliptic equations, I said that you can check it using this ratio that the derivative is positive instead of using decomposition in spherical harmonics. You can just use the definition here and do some integration by parts and derivatives to prove it. And this is a better way because you can extend it to elliptic PDEs. The elliptic second order PDE will always in the simplest divergence form equation. Where A is symmetric with Lipschitz scalar. And uniform derivative. And if you want your integration by parts go through, you want to adjust a little bit the definition of the frequency function, or the definition of the average. We fix once again some like zero, so that we have a solution of this equation ball around the zero. And we introduce the rate function mu as the ratio of the scalar product of x and x with matrix A here over the length of x squared. And then you have to define the average now with this rate. Then for this one, the monotonicity property is not true, but what happens with the corresponding frequency function, and this is now integration by parts, is some struggle. Either this frequency is bounded by constant times the frequency. So the derivative of the frequency in R is bounded. I have to do one more thing that we skipped. I have to change the coordinates such that at this point and 0, the matrix is identical matrix. So if you think what is happening, if you don't want to change the variables, you don't average over balls now, but you take ellipses that are constructed according to this matrix A, 1 and 0. We take averages over this ellipses. And then you have this inequality that basically works as well, more or less as the one that we had before, this monotonicity, so instead of the function. And we can now look at this one times efficient like that, and this is not one function. This looks then R is quite small, this factor is not so much role in this frequencies to recognize not one function. But as I said, I would prefer to stay on the harmonic functions, not to do this adjustments all the time. So the first thing we're going to do is to integrate our frequency, or due to the fact that it's more or less the logarithmic derivative of h. I'll try to improve my community with this blackboard. And I want to integrate pick the lower one. This one. By the definition, this is the integral of the logarithmic derivative of the h, so I get the difference of the log of h of 2. And now we know that this is bounded from the bottom below by the values of the things at the left and point at the right hand point. Find the integral of 1 over r as a whole. If you do this computation, you will get that the following integral is correct. Or I don't know, 2. And on the other hand, it's bounded by the same ratio of the radius to the power of the fragments on the right. And that's why we also think about frequency as a doubling index. We'll look at the average of our functions over the ball and take a double ball. And then we know that this ratio is more or less 2 to the power of the frequency of the function. But to be careful, we have to these frequencies to one that is smaller than the largest radius.
Eugenia.
Yes.
There are some students online that say that the sound is not very good. Maybe if you could talk slowly because of the sound by the internet connection is not great. Just that.
I'll try to talk.
Thank you. Let us see.
Maybe you can ask the microphone. Lower or higher?
I'm not sure I can change my mask right now, but I'll try to talk a bit more slowly or louder if it will help. Let me know if it will improve or not. So, we stop by this inequality, and I want to have a corollary from that. I'll have a harmonic function in the unit ball. I have a frequency of this ball that is fixed, and I want this to make the frequency at some other point. So we take x in the unit ball. R, such as the wall of radius R, have this assumptions of harmonic function in the unit wall. X is the point there, and we take R so that the wall, so that X is R still the wall. And then we claim that the frequency at point X is bounded by some constant and the frequency on the larger scale, say +1, where this constant depends on X and on point, but doesn't depend on the function. It's a relatively simple exercise. First, take point X within the half ball. We know that this function is monotone, so we can estimate it radius that is large enough. I take a point that is in half ball and take radius that this ball contains the origin. Take a bit larger ball centered at X and look at our formula. The averages of our function u over these two balls is more or less the frequency function at this point. X, 0, X, and this part. On the other hand, the small ball is constructed so that it contains a ball around the origin, and the large ball is definitely in the initial one, but we had averages. What you have is what it like that. So this is the larger ball is contained in the original ball for this one. So the smaller ball, it contains a small ball around the origin. And since I have averages here, I have some constants. Constant depending on the ratio of radii height. Here, R2 and 1 and R1 and 2. Take the logs and you get this inequality when X is in the half ball. And then integrate this procedure to the steps and you can get this inequality for any point inside the original ball. In particular, what we know that if we have harmonic function on the unit ball with bounded frequency, then we can estimate the order of vanishing at any point. It could be going to infinity when we go to the boundary, at least if we stay away from the boundary, the vanishing order is estimated by constant times frequency. And the whole lectures will be about what do we know if we have a bound on the frequency of our harmonic function. What do we say about the function? We want to say that it's not too complicated. That bounding the frequency of the harmonic function results in, philosophically speaking, having a complex family of functions that behaves not so bad. But we want more quantitative estimates there. And another thing that we need is to know what to do if we are not inside the domain but near the boundary of the domain. The general answer is nothing, you're lost if you're near the boundary, but there are some particular situations where the things are not so bad. One of them is when your function vanishes from this part of the boundary. When you're near the part where the harmonic function is 0, you can do similar things with the frequency. And now we have a harmonic function given some domain. I'll take x0 that is in this domain on the boundary, and now assume that function b is 0 on the part of the boundary inside ball. This is my pointer. I'm always in some part B. I have a ball and we know the function vanishes here. Then we do the same as before. I think it's better to use the lower frequency here. Do the averages on the balls. This is dangerous, so I'm going to integrate my function to square over the intersection of the ball and the domain, but I will divide over the level. You can think that we extend our function to be 0 here and then take the average. So this is the function h, and the law of frequency as before is this version. And it turns out that the monotonistic property survives. And it's a nice lemma to understand this term. Tells you that monotonicity almost survives. Suppose that our point times 0 is chosen such that this plot is star shaped with respect to x0. Then there is an intensity property. Now suppose that my boundary here is smooth, function is harmonic and continuous up to the boundary of the domain. Zero on this part of the boundary, and this domain is star-shaped with respect to x0. These are the assumptions. And the conclusion is that then, can you see them?
Oh, we can see them.
Okay. I'll put it up. That's the derivative of the law of frequency function.
I think for some reason we read the appearing override, but yeah, that's good.
What does it mean for us? In this work of Kovacs and Nystrom, there is a nice corollary that tells you that the plane shouldn't be too smooth to have some monotonicity of the frequency function. This lemma you can do integration by parts, therefore one. If you have these assumptions, I will probably say my function is not just continuous but C2 up to the boundary to be able to do all the integration by parts with no problems, but then you should be able to check that this is monotone functioning R. And what they also prove is that the frequency function is almost monotone if your domain is C1E. So to do this computation, you want your function to be C2, or you want your domain to be smooth enough, but you can then do the approximation sync and for the following nice result if this is C1 being domain. And all the same as in this lemma, then for n is equal to epsilon, that is R. Doesn't depend on u, but depends on this epsilon. The condition of the uniqueness of the function that defines here, C1 meaning smoothness of the boundary. No, right. The boundary smoothness. What's that? The frequency. Yeah. Is almost monotone. And the smaller wall, the frequency is bounded by 1 plus epsilon times the frequency on the larger. Now let's think about x is 1. Could be on the boundary. We don't need star shape condition. Here, we use this computation of the approximator as symbol. I mean, this is star shape. If your boundary is smooth enough, and you go a bit up here, then for small gradient, this domain is star shape.
You can remember what C1 D is.
It is a little bit better than C1, but less than C2, so I don't want to do it, but I can do it later or in my notes. It will not be very important for us because what we also know, and this is another story of this computation more or less. You find it in Charlotte's work, and give you presentation now later work on Gauss conjecture in your fellow class. Second functions is that if your domain is Lipschitz with small Lipschitz constant, then a bit weaker condition. We have the same assumptions, but the inequality that we get look like that. Here, one values are 1 and 2. The arbitrary less than this R. Here, I have this. So this one is much better because it tells you that there is no blow up, no frequency when you get to the boundary. This one tells you that there could be a blow up, but in a controlled way. It's not worse than geometric series with a small constant. I don't know if this is the best that you can do. I don't have examples of harmonic fractions that vanish on the top of the boundary, this boundary being Lipschitz, which you can show that the frequency actually blows up. It would be nice to see those effects. But what we know is that it doesn't blow up too much. This without to do that in this. I want to.
Is there any component that you call it beyond how the small is constant?
Sorry?
Can you get something like that without the, I mean, maybe something worse without small is constant?
This would be great. I don't know.
Okay.
Yeah. Probably you can get it through the logic with the logic constant. Which is the main logic constant that you can do. I have to check. But probably with the main pieces you know, you want to know that you can make this constant. Close. But it's a good question and I have to Let me go back to the monotonicity property and the inequality for the averages that we had before and reduce. We will see both. I'll first just to write the monotonicity property inside of the domain and write it. The average over all values 2R is bounded by the square root of the average over all values R and the all values 4. It's a particular case of R, of course, in the hybrid. And it tells you that I move just to make the right hand side by the maximum instead of there are 2 norms. And relative them produce harmonic functions or solutions of electric equations. I know that in a big smaller ball, my function is bounded by this average. For instance. So what we'll get is the sum of function over ball, say, values to factor part is bounded. Square here. And it's a version of symbolic quality because if the function is small on the ball inside and you have some upper control, and it's also small on the intermediate ball. We'll need a version of this on the boundary, and there's when the term estimates this one. If you take this, for example, with epsilon that is equal to 2, we can say instead of this inequality, we'll have near the boundary where the function vanishes, inequality like that. So I should take a smaller power on a small ball plus 1, which it says, and then a larger power on a larger. So this almost monotonicity of the frequency function result in such inequalities near the boundary. Use them after the break. This 3-ball inequalities for one function. I want to finish with one remark. The inequality that we got when we integrated our frequency function was like that. The average of all x to r is squared is bounded by the ratio of the radii, that is 2 in my case, to the frequency to this one. And as I mentioned, we now for solutions analytic, it is that we can bound this average from below by the maximum of the small ball. Then what you get here is the reverse Hausdorff inequality. We have infinity norm of the 2-normal function with this coefficient that depends on the difference. And it was also one of the points of the Garfield and Lim, but now you know that the weight is an undefined weight, and you can try to put it as all other conditions for the function being made. One that we will probably mention after the break, and the next lecture is to found the DMO. We know that the function is going to calculate, and the what is DMO. And the question is, can we bound this norm using only the frequency? But you can try to remember all the definitions of we can calculate the TNA and try to see if these conditions can be made quantified by using the frequency. I think we'll take a break till 12:15 and then we'll continue to it. Any questions?